Before we jump into the assertion, it's undeniably more enticing to figure out what subatomic gas pedals are. The Huge Hadron Collider, LHC, worked by CERN, is a 17M ring of superconducting magnets. Likewise, it's the world's most unmistakable and most critical iota smasher. It represents the zenith of human accomplishment. Truly, it's strong to such an extent that it could imitate the exact conditions of the first second on the planet. Yet, could the system expected to open the secret of the universe hold the way to something genuinely unambiguous? Founded in 1954, CERN is one of the world's most renowned examination foundations, with 23 member states and endless specialists. It's a spot for coordinated effort and innovation. The LHC is CERN's chief endeavor, but it is just a single piece of an enormous association of gas pedals and tests. Think about a course, not such a huge amount for vehicles or people, but for subatomic particles. In a preliminary of fitness, persistence, and space itself, the LHC speeds up protons to practically the speed of light, sending them on an impact course that mirrors the energy of the universe just after the Big Bang. The effects create temperatures much hotter than the center of the Sun. A big number of magnets guide the protons on their excursion, while complex cooling structures keep the magnets at temperatures colder than space. The shafts in the LHC are made to crash at 4 areas around the gas pedal ring, connecting to the spots of 4 molecule identifiers: Atlas, CMS, Alice, and LHCb. Each fills a particular purpose, exploring various parts of molecule physical science. Together, they go about as huge cameras, taking photos of these impacts. Scientists then, at that point, scan through the flotsam and jetsam looking for indications of the slippery Higgs boson, also referred to as the God particle, and other irregularities that could give clues about the universe's fundamental building blocks. By zeroing in on the microcosm, we gain insights into the universe. Yet, with each discovery comes another question, and with each revelation, another test arises. The LHC isn't just a scientific instrument, it's a display of human interest and progress. It represents our enterprising mission for knowledge and our craving to grasp the key forces that shape our universe. But as we stretch the boundaries of what we know, we must also consider the more significant and existential questions that arise. What are the risks of testing the unknown? Might our journey for knowledge accidentally release forces we have no control over? Inside the sacred halls of CERN, where the limits of human knowledge are continually pushed, a discovery has emerged that sends a shudder down the spine of even the most supportive of scientists. Brian Cox, a former scientist at CERN and a voice of expertise in the field of molecule physics, has recently offered something that has left the world both fascinated and uneasy. Cox's words resonate with chilling clarity. The reason for CERN's Large Hadron Collider is to reproduce a little Big Bang. Yes, you heard that right. A little version of the very event that birthed our universe. The physicist also proceeded to explain the implications of this point, highlighting the LHC's enormous potential for making new discoveries. This includes its capacity to uncover the secrets of the Higgs boson and investigate dark matter, a mysterious substance that makes up a significant portion of the universe. Imagine grasping the power of creation, the ability to call the very essence of the universe into being. It's an alluring prospect, but one full of risk. The Little Big Bang isn't a hypothetical idea. It's a real phenomenon inside the LHC. The temperatures, the pressures, the raw energy, everything replicates the conditions of the universe's birth. It's like standing at the beginning of written history, witnessing the birth of life itself. But with such power comes responsibility, and the question looms, what if something goes wrong? In fact, something did go wrong back in 1978. Russian physicist Anat Borsky experienced a catastrophe that would forever alter his life. While working on the U-70 synchrotron at the Institute for High Energy Physics in Pino, Russia, a failure caused his head to accidentally enter the direct path of a proton beam. The beam, with a power that challenges perception, went through his skull, entering the back of his head and exiting through his nose. Borsky's experience was terrifying. He saw a flash brighter than 1,000 suns but had no immediate worries. The beam's path resulted in a trail of destruction, searing tissue and bone, yet he remained conscious and even walked to the clinic for treatment. The result was both disturbing and remarkable. The beam caused localized tissue damage, leading to hearing loss in one ear and partial facial paralysis. Remarkably, Borsky's mental faculties remained intact, and he continued his scientific career. This incident serves as a reminder of the immense power and potential dangers of particle accelerators. The risks of a particle smasher like the LHC are not to be underestimated. The potential for catastrophic reactions, the very fabric of existence being altered, these are not the stuff of science fiction, but genuine concerns voiced by respected scientists. One of the most disturbing and fascinating concerns related to the LHC's experiments is the possibility of creating a micro-black hole. Black holes are regions of spacetime where gravity is so strong that not even light can escape. They are massive vacuum cleaners, devourers of stars and strange entities lurking in the shadows of our universe. The fact that the LHC could potentially create such a phenomenon, even on a small scale, is both astonishing to the public and scientists alike. Could this black hole eventually grow out of control, swallowing the Earth from the inside? Scientists at CERN have reassured the public that any black hole created would be unstable and would dissipate rapidly. Nevertheless, the remote possibility has sparked discussions, fears, and a sense of awe at the power we wield. It's important to understand how the LHC could create a black hole. It all revolves around the fundamental mechanics of particle accelerators. When protons are smashed together at nearly the speed of light, the energy released is immense, to the point that it distorts the fabric of spacetime itself. Imagine a trampoline stretched tight, and then a heavy object is dropped onto it. The material bends, and if the object is heavy enough, it could create a well so deep that anything nearby could be drawn into it. This is an analogy for what could occur at the LHC in the realm of quantum physics, where the laws of the universe are both strange and wondrous. There's speculation that additional dimensions may be hidden within our reality. If these dimensions exist, the LHC's experiments could tap into them, creating a gravitational well that forms a small black hole. This bizarre dance of particles has even caught the attention of several renowned scientists, especially the late Stephen Hawking. In his book, he warned of a scenario where the Higgs boson could become unstable at very high energy levels. This instability could lead to a catastrophic event known as vacuum decay, an event that wouldn't destroy Earth, but could potentially annihilate the entire universe. The famous English cosmologist and astrophysicist, Sir Martin Rees, also expressed concerns about the experiments conducted at CERN. In his book on the future prospects for humanity, he examined the potential risks of particle accelerator experiments, including those at CERN. His words weren't cautious, they were filled with a sense of existential dread. He explored a worst-case scenario in which a failed experiment could trigger a phase transition that would ripple through the fabric of spacetime, causing a catastrophe that would engulf the entire universe. Rees' concerns weren't limited to theoretical speculation. He assigned a low probability to these disastrous outcomes. However, he argued that even a small chance warrants serious consideration. Much is at stake, and the margin for error is razor-thin. The scientists at CERN have run simulations, analyzed theories, and taken precautions to ensure the safety of the LHC. In fact, Brian Cox himself emphasized the importance of these measures, acknowledging the inevitable concerns and doubts surrounding the LHC's activities. He reassured the public that there are stringent safety protocols in place, comprehensive reviews, and procedures to ensure that the LHC's operations are carried out with the utmost level of scrutiny. Cox reassured the public that the energies involved are well within what the Earth naturally experiences and that the chances of creating a stable black hole are astronomically low. Even if one were created, scientists say it would be so minuscule and unstable that it would evaporate quickly in a burst of energy, a phenomenon predicted by Stephen Hawking, known as Hawking radiation. It would be a fleeting moment of cosmic wonder, a brief glimpse into the deep darkness, and then gone. Some have taken the idea even further, speculating that the LHC's experiments could open a doorway to another universe or dimension. While this idea is largely dismissed by mainstream scientists, it has captured the imagination of many and become a subject of fascination, fear, or even fantasy. What lies beyond our universe? Might we accidentally release forces or substances that we do not understand, paving the way for catastrophe? This idea has even been sensationalized in various media, stirring up uncertainty. But how did this idea come to fruition, and what does it mean in terms of scientific exploration? The possibility of extra dimensions is not new in physics. String theory, a leading candidate for a unified theory of everything, suggests that there might be more than the usual 3 dimensions of space and 1 of time. These additional dimensions could be compactified or hidden from our perception, but they could, in theory, be accessed or revealed under extreme circumstances. Now, imagine the LHC as a giant key, opening doors that have been locked since the beginning of time. As the LHC continues to probe deeper into the fundamental nature of the universe, scientists remain focused on the potential for groundbreaking discoveries. But even as they explore these mysteries, the questions about the risks associated with such powerful experiments linger. Can we fully comprehend the implications of manipulating the very forces that govern the cosmos? Will the quest for knowledge unintentionally unravel the fabric of reality itself? The possibility of opening doorways to other universes or dimensions, though highly speculative, presents an intriguing philosophical and scientific dilemma. If extra dimensions exist, what are their properties? Could they harbor new forms of matter, energy, or even life that we have yet to imagine? Could these realms have their own set of laws, and if so, how would they interact with our own universe? Many leading physicists are cautious, emphasizing the stringent safety measures in place and the low likelihood of dangerous phenomena occurring. Yet, the questions posed by the LHC and its potential to uncover the unknown remain profound. The LHC serves as both a symbol of humanity's intellectual curiosity and a reminder of the fine line between scientific exploration and unforeseen consequences. For now, the LHC continues to operate, conducting experiments and yielding data that could reshape our understanding of the universe. However, its role as a gateway to some of the deepest mysteries of existence means that the ethical and existential questions surrounding its use will likely persist, prompting continued debate among scientists, ethicists, and the public alike. As we venture further into the unknown, we are confronted with the timeless question: to what extent should we push the boundaries of our knowledge? The pursuit of truth is a noble endeavor, but as we unlock the secrets of the universe, we must also be mindful of the unknown dangers that may lie ahead. The story of the LHC is far from over, and its ultimate legacy will depend not only on the discoveries it makes, but on how we, as a species, choose to confront the consequences of our exploration. As the LHC presses forward, the continued exploration of the universe's most fundamental particles and forces may yield discoveries that could rewrite the textbooks of physics. But with each leap forward in understanding, there is also the potential for new, unforeseen questions and challenges. Scientists must constantly balance their drive for discovery with the understanding that any breakthrough could bring new complexities and risks. One of the most exciting frontiers in particle physics lies in the search for dark matter and dark energy, mysterious substances that make up much of the universe, yet remain undetectable by conventional means. While the LHC's experiments may one day reveal critical insights into these enigmatic forces, the process is slow, and progress is often met with frustration. Still, the implications of such findings could be revolutionary, not just for physics, but for our entire worldview. The discovery of dark matter or dark energy could challenge our understanding of space, time, and the very nature of reality itself. Moreover, the LHC could eventually provide the key to understanding the ultimate forces of nature, such as the